So we've talked about the fact that thrust depends on the cavity Q factor. We've talked about microwave cavities typically having cavities Q values of 50 by 10 to the, or 5 by 10 to the 4, 50,000. But this is the classic microwave cavity made of copper or silver-plated aluminium at room temperature. Now, in any cavity, the Q depends on the resistivity of the walls, and if you can reduce that resistivity, then you will increase the Q. In a superconducting material, the resistivity is reduced close to zero. It's not actually zero, but it is approaching zero. And this means that a superconducting cavity can typically obtain a Q of 1 by 10 to the 9th. Okay, so that's 5 orders of magnitude almost up on what we're getting with our room temperature cavities. This is quite well understood engineering. The typical high energy accelerator will use many hundreds of cavities, all with these sort of values of Q, so that superconducting microwave cavities can be considered even now as a manufactured item, indeed a sort of reasonable high quantity manufactured item. So there's nothing too difficult about those. The problem, of course, is that any superconducting cavity requires cooling. What we propose is that for most transport applications, and indeed for most space applications, we would probably use liquid hydrogen as opposed to the liquid helium which is used in the high energy physics cavities. There's a big advantage in this because using liquid hydrogen to cool cavity means that as you boil off the liquid hydrogen, you can make use of the hydrogen gas in a fuel cell along with a bit of oxygen to produce your electrical power. And in the early designs of space planes, and the one that you'll see, you can see that the hydrogen is also used for auxiliary propulsion. Now this 2G cavity with a vastly increased value of Q gives a step change in the thrust, and the sort of target that we look for is goes up from instead of, if you like, a few grams per kilowatt to a ton per kilowatt. So this then means that you have a propulsion system with a significant thrust to power ratio, one that can be used for all sorts of applications, and I guess the main space application that we're considering is a launcher, a hybrid spaceplane launcher. In fact, the design study that we did showed that we can come up with a 300-ton reusable vertical takeoff and landing launch vehicle capable of putting 50 tons into geostationary orbit regularly on a almost aircraft-like sort of cycle. Now, once you can start launching things into geostationary orbit, or any orbit, using what's basically commercial aircraft type approaches, the cost begins to tumble. You have large numbers of missions instead of the one. You don't throw away the vehicle as you do at the moment, and you have a ground infrastructure which is modelled on an airline rather than on a scientific launch. The impact of this will be that the cost of launching to GEO will be reduced from the current costs by approximately a factor of 130. And this, is, of course, is the thing that makes a significant difference to such a large-scale applications as solar power satellites or any sort of geostationary, geoengineering programs that use in-orbit technology. Okay, so what have we done to prove 2G? Well, we've built an experimental thruster. We've done a lot of design studies on various space planes and other vehicles, and showed that essentially it's all a reasonable extension of existing technology. Okay, so what can it do? Well, first of all, let's look at a first generation. This is a room temperature, uncooled cavity designed specifically for satellites. The short answer is that it should save of the order of £15 billion if you look at the satellite launches planned for the next 10 years, on the assumption that instead of using the traditional launch concept, we use EmDrive to take us from LEO, that's low Earth orbit, up to GEO. If you look at a classic 3-ton communication satellite, what surprises a lot of people is that over half the mass of that satellite is actually propellant. And this propellant is used to take the satellite from its transfer orbit, which is where the rocket puts it, into its operational orbit, which is where it starts making money. So if you can replace the mass of the propellant, or even get rid of the mass of the propellant, you clearly are going to reduce the launch mass and therefore reduce the cost of launch. The reality means that the mass of an EmDrive propulsion system, that's both primary and the so-called AOCS, that's the attitude and orbit control system. If you take the mass, the dry mass of an EmDrive propulsion system, it just about equals the dry mass of the existing propulsion system. So what you're actually doing is you are simply getting rid of the mass of the propellant. In terms of real measurements, you're getting rid of about 1.7 tons of mass from a classic 3-ton satellite. So you reduce the launch mass to 1.3 tons, therefore you use a smaller launch vehicle, or alternatively you can put more satellites on the same launch vehicle. You essentially launch it to low Earth orbit instead of its transfer orbit. You deploy the solar arrays and antennas in low Earth orbit, which is means that you do have at least some chance of recovering them if this goes wrong. Deployment of these arrays and antennas is always the critical thing in the launch sequence of a typical communication satellite. So you've got your arrays deployed, you've got power feeding now into the EmDrive propulsion system, and you can use the thrust to spiral out from LEO to GEO using so-called Edelman transfer in typically 36 days. Once you're in orbit on the station, you can use the technology for station keeping and attitude control, and this means that you no longer are restricted by the reserve propellants for operational life. It does give you the opportunity of having much longer operational life for your satellite. So that's first generation, pretty straightforward. Technology is, if you like, now established. It's just a matter of waiting for industry and the user community to catch up. What is much more exciting and interesting is what a second generation EmDrive can do. and we've actually touched on this before, but the primary application that we see is to make use of it as a propulsion system in a unmanned carrier spaceplane. In essence, we would use a very high thrust EmDrive engine to provide lift to this vehicle, and once it's actually reached geostationary altitude, you would then use a conventional rocket to put the orbital module into orbit with the necessary orbital velocity. You don't actually accelerate the whole vehicle to orbital velocity, you merely use it as a, if you like, as an elevator to get you up to the launch, up to the operational altitude. So what we're saying is that we will use the EmDrive as a lift engine. This will lift the carrier vehicle to the altitude. It will do it gently and efficiently, rather than in the rather brutal manner that is a classic launch vehicle. And once it's at the altitude, then you'll use a conventional rocket to accelerate you up to orbital velocity. Now, because you're obviously accelerating in vacuum by then, you're at 36,000 kilometres. Clearly, it's a very efficient way of getting orbital velocity. Essentially, this gives you a very large reduction in launch cost. It makes for a very simple, low-stress launch vehicle, and the big application that we see is solar power satellites, because suddenly solar power satellites become not only economically viable, they become something like about a tenth of the cost of a nuclear power station for the same electrical output. We've mentioned before that the actual EmDrive cavities are cooled using liquid hydrogen. The gaseous hydrogen is then used in fuel cell to produce the power for the microwave generators, which in turn will provide the thrust in the cavity. But also the hydrogen gas can be used in a conventional small jet engine for in-atmosphere manoeuvring, and used as an input to a rocket engine for in-orbit manoeuvring, or sorry, in-space manoeuvring. So we're talking about a typical atmospheric operation of probably only reaching a maximum speed of around 250 miles an hour. We're going to have very low vertical acceleration of the order of 0.05 of a g. That's about half a metre per second. EmDrive will be used to provide the lift, but also the pitch and roll and yaw control, and we will use a jet for propulsion. Now, this is in the atmosphere. Once you move out of the atmosphere, you then start to accelerate to higher speeds, but again you keep the acceleration levels low. Maximum acceleration we would apply to the vehicle would be something of the order of a 0.32 of a g. EmDrive again is providing pitch, roll and yaw control as well as lift, but now the auxiliary propulsion is provided by a rocket. So once you've reached your orbital altitude, you effectively release the orbital module, and that has again a separate rocket engine which gives you your orbital velocity. And the orbital module itself is not reusable, but the carrier vehicle, which is where all the complex stuff is, obviously is. And essentially you would simply come back to Earth in a reverse sequence to your ascent, and achieve a vertical landing. So your ground infrastructure need be no more than an area not much bigger than a typical car park.